Welcome back to Mechanical Engineering Made Simple. Today we are pushing past those idealized classrooms, where everything is clean, light, and totally friction-free. We are taking a deep dive into the messy reality of mechanical engineering, nonlinearity, instability, and how we actually control vibration when the equations, frankly, refuse to behave.
It's so true. Historically, mechanical analysis really relied heavily on linearization, which is, essentially an indispensable shortcut. We take these complex physical laws, maybe involving fluid forces or large displacement geometry,
Right.
and we simplify them, make them into linear equations that are, well, easy to solve. This gives us a decent first look, an analysis of an idealized system, and it's often close enough, provided the motions stay really small.
But engineering systems, they rarely stay small or tidy, do they? The moment you introduce significant vibration amplitudes or specialized materials that don't quite follow Hooke's law, or think about the critical clearances in high-speed machinery, those clean linear assumptions, they just break down. So our mission today is to unpack what happens when those assumptions fail. We'll look at the really ingenious ways we fight back with vibration control systems, but also the catastrophic failures caused by things like self-excited motion. Okay, let's unpack this. Let's start with the fundamental problem.
Mhm.
Why does linearity fail? Where does it fall apart?
Well, when we're forced to incorporate the full physics of a system, we step into the realm of nonlinear analysis. And what's fascinating here, truly, is that nonlinearity doesn't just tweak the linear answer. It often reveals totally unsuspected phenomena, like brand new behaviors that linear theory simply couldn't predict, not even hint at.
I guess the most accessible example is the simple pendulum, right? If you remember from intro physics, we always assume the angle, theta, is small, so we can approximate sin theta as just theta.
Exactly. That's the linear equation, and it tells you the period is constant no matter how high you swing it, which feels intuitive but isn't quite right. But if you analyze the full exact equation, the one involving sin theta, you find something different. The period of oscillation actually increases as the amplitude increases. That relationship, period versus amplitude, that's a purely nonlinear effect, totally missed by the linear model, but pretty crucial if you're building, say, a highly accurate clock.
And it's not just motion geometry, right? It's materials, too. Hooke's law assumes that perfect straight line relationship. Force equals stiffness times displacement. But real springs or complex structures, they deviate.
Yeah, they do.
Yeah.
And these deviations, we characterize them based on how that restoring force changes relative to the displacement. We tend to classify them into two main types of stiffness characteristics.
Okay, what's the first one?
The first is the hardening characteristic. This happens when the restoring force ramps up more rapidly than the displacement. Think about a coil spring, where the coils actually start closing up, touching each other. The force needed to compress it further just skyrockets, right? Mathematically, we often model this by adding a cubic term, an x-cubed term, with a positive sign. It makes the stiffness curve sweep upward.
Okay, hardening. Makes sense. So the opposite.
Conversely, yes, we have the softening characteristic. Here, the restoring force increases less rapidly than displacement as the amplitude grows. We actually just saw this with the pendulum example. The larger the swing, the less effective that restoring gravity component becomes, relatively speaking.
Right.
And this is modeled using an x-cubed term too, but this time with a negative sign. It makes the curve sweep downward. That x-cubed term is particularly useful because it maintains the physical symmetry. The restoring force acts the same regardless of the direction of displacement.
And crucially, I think this is important. Even if all your individual components are perfectly linear, the system itself can still become nonlinear, just through geometry or physical constraints. The source material highlights something called snubber action. Like imagine a mass oscillating linearly until it hits a rigid stop.
A hard limit.
Yeah. That collision instantly changes the stiffness profile. It leads to what's called a piecewise linear characteristic. So the overall system is now behaving non-linearly, even though the internal components are all, clean linear springs.
Exactly. The system behavior emerges from the interaction.
So, okay, if we accept the real world is messy, non-linear, the engineer's first job is often control. We have systems constantly getting hit by some persistent external harmonic force, what we call forced vibration. How do we fix it? The approach seems to be introducing auxiliary mass systems.
That's right. And there are two main strategies here, really depending on whether that excitation frequency is constant or if it might vary. The first solution is the dynamic absorber. This is used only when the excitation frequency is precisely known and doesn't change. It's basically just an auxiliary mass attached via a spring, and it's tuned very precisely, exactly to that excitation frequency.
And here's the aha moment, the mechanism that makes it so clever. When that absorber is perfectly tuned, it effectively creates a point of no motion, a node right where it attaches to the main system.
It forces it to be still.
Exactly. It works because the force generated by that absorber mass oscillating, which is F equals omega squared on aught, the mass times frequency squared times the absorber amplitude, that force, exactly, cancels out the incoming external force. So the primary mass. It just stays perfectly still. It's quite elegant.
It is elegant, but the limitation is, well, severe. As soon as that incoming frequency shifts even a tiny bit, a fraction of a percent, the absorber stops absorbing. Worse, it can actually bring the entire combined system into a dangerous new state of resonance.
Oof. So it turns the fix into a potential disaster.
Pretty much, if the conditions aren't perfect.
Okay, here's where it gets really interesting, because that brings us to the more robust solution, right? The auxiliary mass damper, or sometimes called a damped absorber. This system adds a viscous damper element between the auxiliary mass and the primary structure. That makes it effective, even if the excitation frequency wobbles a bit.
That's the key improvement. And the optimal design for this system relies on a really clever insight you get from plotting the frequency response curve. When you vary the damping parameter, zeta, in a damped absorber system, the response curves for different damping values all intersect at two specific points. We call these locations fixed points, usually labeled A and B.
Fixed points. And why are they so crucial?
Because the vibration amplitude at those 2 points is completely independent of how much damping you apply. Think about it. Normally, adding damping lowers the vibration curve everywhere, right?
Reduces the peaks.
But at points A and B, the amplitude just stays put. Doesn't matter how much you tweak the damper. So the engineer's goal then becomes setting the optimal tuning ratio, alpha opt, so that the amplitude at point A is exactly equal to the amplitude at point B.
Ah, you level them out.
Exactly. Because by leveling the response at these two crucial damping-independent points, you essentially guarantee that the maximum peak response the system will ever hit across a range of operating frequencies is minimized. You're actively designing for the flattest, safest possible response curve.
That optimization. That's how heavy industry keeps things stable then. And this isn't just abstract theory, is it? This is what powers real-world things like ship anti-roll systems. They use tanks of fluid pumped around, or sometimes massive gyroscopes.
Right, acting as auxiliary masses.
Acting as auxiliary masses to counteract that persistent rolling frequency the ship experiences from waves. That's forced vibration control in act.
Precisely. So, okay, if we connect this back to the bigger picture, we've been talking about forced vibration, something driven from the outside. Now we need to shift gears to what is arguably the ultimate danger in mechanical systems: self-excited vibration. This is fundamentally different and often far, far more destructive.
How is it different? What's the core idea?
In a self-excited system, the alternating force that sustains the motion is actually generated or controlled by the motion itself. If the system stops moving, the force just disappears entirely.
Okay, so the motion feeds the force that causes the motion, a feedback loop.
Exactly. It's why the source material explains it mathematically as being analogous to negative damping in a linear system. The solution involves an exponentially increasing amplitude. It heads straight towards instability and, likely, system failure.
And the most critical place this shows up is in high-speed rotating machinery.
Yes, leading to whirling and whipping of shafts. Think jet engines, turbines, pumps. This instability is driven by a tangential force. It acts normal, or perpendicular, to the radial deflection of the shaft. And crucially, this force is proportional to that deflection. So the more it deflects, the stronger the driving force. It acts like a little engine continuously feeding energy into the whirling motion.
And it overcomes the natural damping in the system.
That overwhelms any external damping,
Yeah.
causing the shaft to spin out of control, basically.
Now, what's vital for you listening to grasp is the diagnostic feature. How do you tell this apart from just simple imbalance, which is also common?
Good point. In self-excited whirl, the whirling motion happens at the shaft's own natural or critical frequency. And here's the kicker. That whirl frequency is entirely independent of the shaft's rotational speed, the RPM.
Okay, so if the machine spins faster or slower, the whirl frequency stays locked onto the system's natural frequency.
Exactly. Whereas vibration due to imbalance is always synchronous. It happens at the rotation frequency. And here's the profound danger. Simple Synchronous force vibration. From imbalance, it's bad,
Yeah.
but somewhat predictable. The stress on a given point in the shaft is constant as it rotates.
Right.
Self-excited whirl induces intense alternating stresses. As the shaft whirls, the metal fibers on the surface are constantly being bent and straightened, flexed and relaxed at the whirl frequency. This leads to rapid, catastrophic fatigue failure. That stress reversal is far more damaging than the constant stress from synchronous unbalance.
That makes sense. Rapid cycling breaks things faster. So let's quickly run down the common culprits, the mechanisms behind this self-excited instability in machines.
Okay.
First, there's hysteretic whirl. This is caused by internal friction, material hysteresis, like within the shaft material itself, or maybe in shrink fits or joints.
Internal damping, but acting the wrong way here.
Right. This internal friction causes a tiny phase shift between the bending stress and the strain as the shaft flexes. And this results in a small residual tangential force that drives forward, whirl meaning whirling in the same direction as the shaft rotation. Crucially, this type usually only kicks in once the shaft speed gets above its first critical speed.
Correct. Needs enough speed to overcome the stabilizing effects.
Okay, second, highly common, especially in power generation.
That would be fluid-bearing whip, or sometimes oil whip. Here, the viscous fluid, the oil circulating in the bearing clearance, creates asymmetric pressure forces as the shaft moves off-center. These generate a powerful tangential force, because the fluid usually circulates at roughly half the shaft speed.
The famous half-frequency whirl.
Exactly. This instability typically requires the shaft RPM to be greater than or equal to twice its critical speed before it really kicks in. It also causes forward roll.
Got it. And finally, the really scary one, dry friction whip.
Yeah, this is often called rubbing. It's a terrifying event that happens when the rotating shaft actually makes physical contact with a stationary part like a seal or maybe the stator casing. The resulting Coulomb friction generates a tangential force. It's highly sensitive to the contact conditions, but it often induces backward whirl.
Backward whirl, so whirling against the direction of rotation.
Yes. You can almost picture the shaft trying to roll or climb along the static boundary it's rubbing against. Very destructive, very quickly.
Okay. We've seen control methods, we've seen these catastrophic self-excited failures. Let's wrap up by looking briefly at what happens when you bring nonlinearity back into a forced system, even one that might seem stable initially. You get these strange, multi-valued responses and ultimately chaotic behavior.
Right. One of the absolute hallmarks, especially in systems that have that hardening or softening stiffness we talked about, is the jump phenomenon. Remember those stiffness curves that sweep up or down? When you plot the force vibration response for these nonlinear systems, the resonance peaks aren't symmetric anymore. They get significantly swept over to the right for hardening systems and to the left for softening ones.
So what happens if you're operating near that bent-over peak?
Well, let's say you slowly increase the frequency of the external force on a hardening system. The vibration amplitude rises along the curve. But then instead of smoothly following the curve over the top, it hits a point where the curve becomes vertical, a point of vertical tangency.
Okay.
At that exact point, the system physically cannot sustain that high amplitude state, and it will suddenly, instantaneously jump down to a much lower stable response level on a different branch of the curve.
A sudden drop in vibration.
Exactly. And conversely, if you then slowly decrease the frequency, the system stays on that low amplitude branch until it hits a different point of vertical tangency, forcing it to suddenly jump up back to the high amplitude branch.
Wow. So there's a whole range of frequencies where you can be in either a high vibration state or a low vibration state, depending on whether you got there by increasing or decreasing frequency.
Precisely. It reveals this critical aspect. In that frequency range, there are often three mathematically possible solutions for the amplitude. But that intermediate solution, the one connecting the jump points, it's fundamentally unstable. The system cannot physically operate there. Any tiny disturbance forces it to jump to one of the stable high or low states.
That has huge implications for design and testing, I imagine. And the ultimate breakdown of predictability, sort of the final frontier mentioned in the source material, is chaotic dynamics.
Yeah, chaos. Chaotic vibrations are characterized by waveforms that look, well, irregular and non-periodic. The pattern never actually repeats itself. But the defining feature, mathematically, is extreme sensitivity to initial conditions. If you start a chaotic system twice, with starting points that are almost identically the same,
Infinitesimally different.
the resulting motions, the solutions, will diverge exponentially over time. They become completely different. This means they are inherently unpredictable in the long term. Long-term forecasting or control becomes essentially impossible.
Sounds like just random noise then.
It looks like it sometimes, but there's often hidden structure. And engineers have found ways to visualize this. The main tool is the Poincaré section. It's like using a strobe light on the motion. You plot only the displacement versus the velocity, but you only take a snapshot, a single point, exactly once per cycle of the external forcing function.
So you're sampling the state of the system at regular intervals based on the driving force?
Exactly. And instead of getting a completely random smear of data points, which is what you'd expect from truly random noise, the Poincaré section of a chaotic system often reveals these striking, intricate, but definitely structured patterns. These complex bounded structures are called attractors, sometimes strange attractors. They give us insight into the boundaries and the nature of the chaotic motion, even if we can't predict the exact path. It helps us understand the limits of the chaos.
That journey, then, from the simple linear ideal of a pendulum through precise vibration controls like dynamic absorbers and damped absorbers,
No.
all the way through self-destruction from whirling and whipping and landing in outright chaos, it really reveals just how much hidden complexity lies beneath the surface of seemingly simple rotating machines.
Absolutely. This raises an important question. We often think about mechanical stability purely in terms of damping. Right. Does it dissipate energy? But the stability of even a simple periodic motion in a really complex nonlinear system,
Yeah.
it might be governed by much deeper concepts, like Mathieu's equation, for example. That equation specifically characterizes whether small deviations away from a known periodic motion will grow exponentially or decay back.
So the final thought for you, the listener, is maybe this. You should think about the stability of any mechanical design, not just in terms of whether it dampens external forces effectively, but ask, if the system deviates just slightly from its expected motion, does that deviation push it towards exponential instability or maybe even into chaotic behavior?
No.
Understanding that inherent fragility, that potential for small errors to cascade, that's maybe the true deep dive takeaway here.
Absolutely. The engineering challenge is always recognizing that while our linear models get the job done, maybe 99% of the time,
Yeah.
the catastrophic failure often lies hidden in those nonlinear terms we initially ignored.
We really appreciate you joining us for this deep dive. We'll see you next time on Mechanical Engineering Made Simple.